To start our discussion of conditional probability, consider the probability that a house gets flooded during a given year. And ask yourself whether you would expect that probability to differ if you only consider houses that were located in a floodplain. And I think the answer to that is clearly that yes, we would expect that to be different because houses in a floodplain would be more likely to flood than houses in general. Now, let's look at an example involving cards. What is the probability that we draw a jack if we draw a single card from a standard deck? Well, we know that all the cards are equally likely. We know there are 52 possibilities in our sample space. So if J is the set of all jacks, then the probability of getting a jack is going to be, there are 4 jacks, so 4 over 52, or 1/13. Now, let's put a restriction on our cards and let's give some new information. Let's assume that we know we have drawn a face card. Okay, so in that case, what is the probability that it is a jack? What we've essentially done is changed the sample space. So instead of being all 52 cards, our sample space is now the set of all face cards. So that'll be the king, the queen, the jack of each suit. And so how many of these are there? Well, there's 3 in each suit times 4 suits, so 12. How many are jacks? 4. So my probability of getting a jack given, okay, so here's some new terminology. This is the probability of J given F. We indicate the given with a vertical bar. So this is going to be the number of jacks divided by the number of possibilities, which is now going to be the set of all face cards. So 4 jacks, 12 face cards, so our probability is a third. In other words, a third of all the face cards are jacks. So that answer seems reasonable. Here is a definition for conditional probability, which we've just seen an example of. Probability of A given B denotes the probability that A occurs given that B occurs. And that probability will be the probability of the intersection of A and B divided by the probability of B, the given. The way that I remember this is the probability of the intersection divided by the probability of the given. That's the way I say it to myself in my head to make sure that I remember this conditional probability definition. Okay, so now let's use this definition to verify what we've already found about the probability of J given F. So J intersect F is the set of all cards that are jacks and also face cards. Well, how many are those? Well, that's the jack of clubs, jack of diamonds, jack of hearts, and jack of spades. There's 4 of them. Okay, and how many face cards are there? There are 12. So the probability of J given F is equal to the probability of the intersection divided by the probability of the given. What's the probability of the intersection? Well, there are 4 cards in the intersection. How many cards altogether? 52. What's the probability of F? Well, there are 12 out of 52 that are face cards. So we end up with 4 over 52. We're switching to multiplication. That gives me 4 over 52 times 52 over 12. You'll get good at simplifying these. 4 12s So 1/3, which matches what we had done before simply by changing our sample space. Here's another one. Let's draw a single card from our standard deck. What is the probability of drawing the ace of diamonds given that the card is red? Okay, well, let's let A be the set that only includes the ace of diamonds, and let's let R be the set of all red cards. Okay, and so then what is the intersection of these two? Well, it has to be an ace of diamonds, but it also has to be red, and so the ace of diamonds, of course, is the only card that qualifies. To find the probability of A given R, we need the probability of the intersection divided by the probability of the given. Okay, once again, our sample space will be the set of all the 52 possible cards. So the probability of the intersection will be 1/52. The probability of red card, well, how many of the 52 cards are red? 26 of them. The hearts and the diamonds, or half the cards, are going to be red. Simplifying this, we get 1/26. This meshes with what we would think of if we just changed our original sample space. We could choose our original sample space to be anything we like. So if instead of thinking the original sample space as being the 52, all the 52 cards, we can think of it as just being the red cards. So we just start with those and we pretend there are no black cards. Well, how many of them qualify to be in the set that we want? 1. How many cards do we have in our sample space? 26. What's our probability? 1 divided by 26. So that's the same thing that we get by doing it with the conditional probability definition. Let's look at another one. Let's roll a single die and consider the probability of rolling a prime given that the number rolled is even. So let's let P be the set of primes that are on a single die. So that'll be 2, 3, and 5. Let's E be the set of even numbers, which will be 2, 4, and 6. And of course our sample space is going to be the 6 numbers that we can get upon rolling a single fair die. 1, 2, 3, 4, 5, 6. We need to find the probability of prime given that the number is even. So that'll be P given E. The first thing you want to do is determine and write in correct notation using our conditional probability symbol. We want to write down correctly what the problem is asking for. Here we want the probability of P given E. Then we remember that this is going to be the probability of the intersection divided by the probability of the given. Okay, so we need to figure out both of these. Well, what's the probability of the intersection? Well, P intersect E is the set of all numbers that are in both P and E. And it looks to me like the only one that qualifies would be 2. 2 shows up in both sets, and it's the only one. Okay, and our sample space has 6 in it, so the probability of P intersect E will be 1/6 because we have one number out of the 6 possibilities. What's the probability of E? Well, we have 3 numbers, 2, 4, and 6. 6 possibilities. So here we get 1/3. Again, this is the same answer that you would get by simply modifying the sample space and thinking of our sample space as all the even numbers that can appear on one roll of a die. Here's another example. In a test conducted by the Army, it was found that of 1,000 new recruits, we have 680 men and 320 women. We have 57 men and 3 women that are colorblind. given that a recruit selected at random is colorblind, what is the probability that that recruit is a male? So let's define some sets. Let's let M be the set of males, and let's let C be the set of colorblind individuals. And let's write down what we are attempting to find. What do we know for sure about this recruit that we have randomly selected? We know that this recruit is colorblind, given that a recruit selected at random is colorblind. And then knowing that, we are asked to find the probability that that person is a male. So we are being asked to find the probability of male given colorblind. Once you write this down, then we can use the definition to write a formula for it. So this is going to be the probability of the intersection of those two events divided by probability of the given. Now we need to find each of these. Okay, so how many are in M intersect C? So these people have to be both male and colorblind. Well, which ones are they? Male and colorblind. Looks like these 57 people are male and colorblind. And how many are in C? In other words, how many are colorblind? Okay, well, that looks like these 57, and then who else is colorblind? These 3. Okay, so that is going to be then the 57 plus the 3 women, so 60. And how many are in our sample space? 1,000. Okay. So probability of M intersect C then will be 57 out of 1,000. Probability of C would be 60 over 1,000. So we end up with 0.057 over 0.060, or 57 over 60, which is equal to 0.95. Okay, that's our probability that the recruit is a male, given that the person is colorblind.